Well, welcome back to SanfordFlipMath. This is AP Calculus. We are doing a lesson on 2.2, which is limits involving infinity. This could be pre-calc toward the end of the year, or it could be continuing with advanced placement calculus, reviewing chapter 2 from last year. So we're going to talk about any limits involving infinity, and so we're talking about something like this where we see x is approaching infinity, or we see this where the actual answer for the limit involves infinity also. Okay, so what I want to do is just kind of give a quick little graphical example, just a little picture so we can talk about this, in a meaningful way. And you should recall that this notation should look familiar. And so if we're talking about x approaching infinity, keep in mind we were talking about going to the right. As x values approach infinity, we're going to the right. So all we're saying is, where do we go? Toward what value are we going? Now, keeping that in mind, this does not approach a number. Okay, so this is actually not going to be a horizontal asymptote. Okay, but it is certainly like end behavior. Okay, so let's do a little sketch of one that will have a horizontal asymptote. So something like this. Okay, so if you note, again, here's that end behavior going. We're going way, way, way to the right, way, way to the right. And if I put a little number on here, let's just say we are approaching 1. Okay, so the limit as x approaches infinity of whatever this graph is 1, whatever this equation is. Okay. Similarly, as we approach negative infinity for x, okay, looks to me like we're still approaching that same value. So the limit as x approaches negative infinity of f of x equals 1 also. Now what this definition says is if we're approaching a number, going to the way to the right or way to the left, if we approach a number, then we have a horizontal asymptote. Notice it doesn't have to be a horizontal asymptote on both ends. It just needs to be one or the other. Now, like the example we just saw, certainly they could have the same end behavior, could go to the same value on both ends. Now, going 100 years back in time, and I don't know if you'll recall this or not, but back in pre-calc, chapter 3 actually, we worked on something called a logistic growth function. That's really rough. And the equation looks something like c over 1 plus a beta of the x, something like that. And you might recall this y equals c was the limit to growth, y equals 0 was the other horizontal asymptote. And so, again, we're talking about this situation where to the right, okay, so the limit as x approaches infinity, in other words, to the right, it approached whatever that value of c was. So c might have been 20. Okay, if that's true, then that would be 20. Okay. And on the left end, the limit as x approaches negative infinity would equal 0. Okay, so in other words, as we're going these way, we're approaching 0. Okay, so if the left end behavior goes to a number, then there's a horizontal asymptote. If the right end behavior goes to a number, then you still have a horizontal asymptote. And again, they don't have to be the same on both ends. They don't have to have a horizontal asymptote kind of thing going on both ends. Just one end or the other is sufficient. Okay? All right, well, inversely or conversely, whichever it is, if your y values approach infinity, coming from a limit, okay, notice this says from the right, and this says from the left. And again, this is an or. If your y values go to infinity, as you're approaching a number in the x value, then that would be an asymptote. So for instance, let's say I have y equals 1 over x plus 2. Okay, graph looks something like this, very rough sketch. You can confirm that in the calculator if you desire. Okay, so if I approach, okay, so this is my a, this negative 2 is my a. Okay, talking about that little a right there. Okay, if I approach negative 2 from the right, notice the y values are going to infinity. So in this case, the limit as x approaches negative 2 from the right was infinity. Okay. Okay, so this is using limit notation to describe that asymptote, and I'm going to do a little bit more also. Okay, the limit as x approaches negative 2 from the left of that y value was negative infinity. Okay, so this is using limits, okay, and that I was talking about this one. Okay, so sometimes you're going to see a question that says something clever like, use limits to describe the asymptotes for this equation. Well, this equation actually has two asymptotes. This describes the vertical asymptotes, sorry. And the horizontal asymptote, much like before, limit as x approaches negative infinity of f of x is 0. Limit as x approaches positive infinity of f of x is 0. So that's how you, so this would describe the horizontal asymptote, sorry, doing that. Okay, so vertical asymptote described here, horizontal asymptote described here, both using limits. Okay, we have one more thing to talk about for this section. It's called an end behavior model. And an end behavior model is basically saying, is basically describing a simplified version of the function with the same end behavior. That's kind of the English version. Okay, the more conceptual way to talk about it. Now, we're giving a very precise definition here using limits, and the idea is that if you do a ratio, now notice here's your end behavior, all right, going to the right, going to the left. Okay, so this is left, this is right. Okay, this is left, this is right. Okay, the idea is if I did a ratio of those two functions, it should be 1. Now, when is a ratio 1? Well, basically when the numerator and denominator are equal. Okay, so that means f of x and g of x need to be about the same, or approaching each other, or something like that, as we go toward infinity. Now, worth noting that this is not going to be true necessarily when we're not approaching infinity or negative infinity. Okay, so here's a quick example. Let's say I have y equals x squared plus 2x plus 1. Now, most of you can just look at this equation and know what the end behavior is going to be. So most of you know that this is going to be a parabola. Because the leading coefficient's positive, it's going to open up on both ends. And I know some stuff's going to happen here. And remember that we're talking about the ends. Okay, so on the left end, it's going up. On the right end, it's going up. Well, how did I know all of that before I even started plotting points or whatever? What basically told me the shape of this graph? So what I keyed in on was this x squared. I knew that both ends went up because it was the leading term. So for me, y equals x squared is the end behavior model. Well, for which end? Well, it's for both. It's for the left end and the right end. Sometimes that happens. Oftentimes that happens. So it's kind of like, you know, is there a big chunk of this equation that really establishes the shape on the ends? So again, obviously end behavior model is talking about ends. Is there a big chunk of the equation? I know that's not very mathematical, but sometimes you have to make things more real, I guess. Is there a big chunk of the equation that makes this thing, that tells us what the n's are going to do. Okay? Okay, another quick example. Y equals 1 over x plus 2. Okay. Well, I know, because of the work we've done with asymptotes before, I know that this is the same thing as 0x over x when x, for when x approaches infinity or negative infinity. In other words, if I'm looking for a horizontal asymptote, I know I can match up those terms of the highest exponent for any rational function. I can match up those terms and get a sense of what is happening for the horizontal asymptote. Well, the horizontal asymptote, as we just discussed a minute ago, is about n behavior. So if this really came from y equals 0x over 1x, which is 0, then isn't our n behavior model for this really just y equals 0? And again, that's for both n's. Okay, so that's the vocab for this lesson. That's really that's the heart of this lesson. Let's see if we can look at a couple more examples. Okay. All right. So this is an example. This is this graph. I found this somewhere on the internet. I don't remember exactly where. And we're talking about an equation of the form y equals a to the x plus b. Now, just to make this a little more real, we're going to do a little specific example of 3 to the x plus 1, okay? And we're going to do all of the asymptotes and also the n behavior models, okay? All right, so here we go. Well, first of all, can you see any horizontal asymptotes? Well, isn't that nice? This is what I call service right here. They actually gave us the horizontal asymptote. That was so sweet of them. What you may recall is if you have something of the form a to the x, or you might remember this is like a times b to the x. The rough sketch of this, if a is bigger than 1, is right here. It's increasing everywhere, and there is a horizontal asymptote at y equals 0, and it goes up to the right. Well, this has shifted up b, whatever b is. So this has shifted up 1. Remember that whole outside-inside thing. If it's addition or subtraction, it shifted up, or it slid left, right, up, down. And if it's outside, in this case that'd be outside of where x is, then you do what it says. Okay, so this said plus 1. If it's outside, it's vertical. So vertical, do what it says, up 1. Okay. Well, that also means that if this used to have a horizontal asymptote at y equals 0 and it went up 1, now there's a horizontal asymptote at y equals 1. Okay, so if I'm going to use limits to describe that, the limit as x approaches negative infinity of f of x is 1. That's not the case going to the right, and I don't see any vertical asymptotes. Okay, so there is a horizontal asymptote, it's y equals 1, and using limits to describe it, its limit as x approaches negative infinity of f of x equals 1. Okay, so horizontal asymptote done. Again, no vertical asymptotes. Okay, so we can just be done with that. And now the only other question is there a right n behavior model? Is there a left n behavior model? Well, what I'd like to do is deal with the left n behavior model first, since I have some information about that right here. And again, the idea, if I think in terms of that ratio as x approaches negative infinity, the ratio of these two functions, so I have some function I know. Okay, so like f of x. Okay, here it is. The idea is if I do a ratio and do a limit as x approaches infinity, I want this to be 1. Now remember that that's only going to work if f and g are about the same when we go way to the left. Well, the other, remember my conceptual thought on this. What is the big chunk of this equation that tells us what's happening on the left end? Well, I mean, isn't it just kind of becoming like that line? So the left end behavior model for this is really just that plus 1. It's that 1. So it's y equals 1. Or if you want to call it g of x equals 1. okay, since they specifically put that g of x in there. If I do the limit as x approaches negative infinity, and I'm probably almost never going to do it like this, of 3 to the x plus 1 over, okay, so I'm building that idea from the definition here, okay, over just 1, wouldn't this limit be 1? And now this is a different one than this one and this one. This is the one that comes from this ratio being the same as we go way to the left. Okay? So the left end behavior model, remember, is just a simplified version of this equation that gives us that has the same end behavior as the other end. Okay? Right end behavior model. Same idea, just the right end. Okay, so focus on this thing going way up. Well, what kind of a function goes way up to the right like this that looks kind of like something from here? Well, again, we're looking for big chunks of the equation. Okay, the simplest version, though, that has the same end behavior. Okay, so what we're hoping to find is maybe just an extra term in there. I'm going to switch colors. So notice, like, here's that 3 to the x. That I've already used the plus 1, so I'm guessing probably 3 to the x. And remember this idea that we talked about from the beginning. If this is a to the x and that it's that shape, going to the right, it's going up. Again, that's if the base is bigger than 1. Well, that's this. Well, so I'm going to say this g of x, to fit this definition, this g of x would be 3 to the x. And again, that's the right end behavior model. Okay, so if I just graph y equals 3 to the x, it has the same end behavior on the right as this one, okay, as the original. Okay, that's it. Okay, shall we do another? I think we have time. Yep, let's go. One more in. Okay, all right, so let's find all the asymptotes. This equation, the equation that I believe they're using for this is right here. Okay, now if you go back to the beginning of pre-calc, you can identify asymptotes just by looking at the equation. And so we have vertical asymptotes from the denominator, x equals -2, and again, x equals +2, so the domain doesn't include those, but those are the vertical asymptotes. Okay. And horizontal asymptote, again, comes from matching up x squared with the x squared in the numerator. Well, there isn't one, so I'm going to put in a 0x squared. And if I do that ratio then, that's 0x squared over 1x squared equals 0. Now, there is a more calculus approach to this, and it's going to feel like overkill. I'm going to go ahead and just buzz through it real quick. But the idea is if you divide the top and bottom by the highest exponent, and so in other words, we're going to do x over x squared. We're going to do x squared over x squared minus 4 over x squared. And let's do some little simplifying here. 1 over x, 1 minus 4 over x squared. Now the idea is once you do that, if you do the limit as x approaches infinity of that whole thing, the simplified version, well, as x approaches infinity, this fraction becomes 0. 1 becomes 1, doesn't change. 4 over x squared, as this denominator gets huge, it goes to 0 also. So this whole thing ends up being 0 over 1 minus 0, 0 over 1 minus 0, which is 0 over 1, which is 0. Well, that's the logic that really gets us to here. That's calculus that gets us here. And our little shortcut that we've been using since pre-calc is match up that highest degree term, and that's what gets us there. All right, so let's use limits to describe this. The limit as x approaches negative infinity, horizontal asymptotes are about end behavior, of f of x is 0. Okay, watch me be sneaky because you know me. The limit as x approaches positive infinity of f of x is also 0. Okay, so that's done. Okay, so we're using limits to describe the asymptotes. Okay, for the vertical asymptotes, the limit as x approaches -2 from the left, -2 from the left is negative infinity. This is going to be long. The limit as x approaches +2, positive scribble, +2 from the right is positive infinity. Okay, we have described the vertical asymptote at -2 now. Okay, we still need to describe the vertical asymptote at +2. As x approaches +2 from the left, I'm just going to go ahead and write down the start of this for both. Okay, +2 from the right. All right, now let's go pop back and look at the graph. Okay, +2 now. From the left, negative infinity. From the right, sorry, I'm running out of room up there, positive infinity. Okay, and then the last thing to deal with is the left and right end behavior models. All right, I'll switch to blue. Left end behavior model. Well, on the left, isn't this approaching 0? And there it is. And on the right, isn't this approaching 0? I mean, when you have a horizontal asymptote, the end behavior models are going to be that horizontal asymptote for that end. Okay, well, I think we're going to leave it at that, and in class you'll have opportunity to do more examples and to ask questions. And remember, if there was anything confusing, go back. Just a reminder, you can pause at any time, rewind if you need to get a snack from the fridge or whatever, you know, that's the beauty of this. Okay, thank you very much. We'll see you in class.